Hi, in this video I'm going to discuss bond polarity. This is really a lead-in to a discussion of intermolecular forces, or IMFs. And before we can start looking at determining whether a molecule is polar or not, etc., we need to understand a little bit about bond polarity. So are there polar bonds present in the molecule or not? So when we talk about bond polarity, the only kinds of bonds that we're really considering here are covalent bonds. So in covalent bonds, the atoms are sharing electrons, usually to get to an octet. Hydrogen, to a duet, it's happy with two. But covalent bonds, they share electrons. Now, they don't always share equally, though. Some elements are electron hogs, and some are happy to let the other ones take the electrons more than they, want them. So there's an unevenness in how much they pull, they exert a force on those electrons. And what that depends on is the electronegativity of the atoms. So we can use charts to look at electronegativity values, and we could go the real strict route. Strict definition is that a covalent bond is polar covalent. So it's going to be a polar covalent. Oh, let's erase that. Polar covalent bond if the electronegativity differences difference is greater than 0.4. Now, the problem with that is you might not always have in front of you the chart of electronegativity values, and for what it's worth, those values are unitless, and they're just for those are relative values, help us to understand the differences between the atoms of each element. But in this arbitrary scale and unitless number, a difference of greater than 0.4 leads to a polar covalent bond. That said, there is an upper bound on it. Okay, so if the electronegativity difference right here is greater than or equal to 2, the bond is ionic. Okay, so anyhow, that's how we define those things. And in an introductory chemistry class, when you start looking at that table of electronegativity values, you'll realize that the true picture of chemical atomic interactions is maybe a little bit more complex than you've learned, and that's okay. Take higher chemistry level courses in college and you'll get there. But generally speaking, greater than 0.4, it's a polar covalent bond. If it's greater than 2 or equal to 2, that difference, then it's ionic. Okay, so this is just sort of all the background. Let's put this in some practical terms and what this means. So let's do an example. So if we have an example here, and we look at not an entire molecule, but just a single bond now. If we look at a carbon-hydrogen bond, for example, we look up the values on the table, and I'm probably going to get these wrong. So let's take a look at it. Electronegativity, just looking it up. For hydrogen, the value it shows as I look at this is 2.2. And for carbon, I see 2.6 about. Okay, so with the difference of 0.4, conclusion that this is a non-polar covalent interaction. Okay, second example. Example 2. Let's say we have a fluorine hydrogen interaction. Hydrogen, it hasn't changed. It's still 2.2 as an electronegativity. But fluorine in this example is up at, do I have the right color? Yep, it has 4.0. And so its difference here is 1.8. So this means that it is a polar covalent interaction. So keep in mind here, remember we're not looking at whole molecules, we're just considering individual bonds first. Once we understand whether individual bonds are polar covalent or non-polar covalent, then we can start considering like the three-dimensional geometry and how that's going to impact what's going on in the whole molecule. All right, and so that's what you got to do with polar covalent bonds. You know, if there are no polar covalent bonds present in a molecule, spoiler here, it's nonpolar. That molecule is nonpolar. If there are polar covalent bonds present in the molecule might be polar. And so you need to consider the three-dimensional structure of it before you can make that conclusion whether or not the molecule is polar.